Right. Good afternoon, everyone. My name is Daniele Mitri, and I'm very glad to see such a full room. And today I will present Learning Pulse, the work that me and my colleagues at the Open University of the Netherlands we have done. And I hope this will inspire you a little bit. So Learning Pulse is a machine learning approach for predicting performance in self-regulated learning using multimodal data. I will first talk about the background of our research, so the context and the vision. And of course, I want to explain about our approach and the data collection, analysis, and the conclusion we can draw from it. So the first thing is that we are into what we call data delusion education. So we can now use, as we have seen today in the presentation, several different sensors in the educational context, such as Fitbits. We can connect from the data we can collect from the MOOCs and from the online learning systems. And these make up now this big data in education. And one of the 5 predictions that IBM, for example, has made is that in 5 years of time, the classroom will be able to learn so their learners. I also found particularly meaningful this image that shows how learning is happening everywhere. Collecting learning experience is a way now of tracing learning. Learning happens across different spaces, so it doesn't only happen online, but also happens where the learner is, in the physical space. At the same time, learning happens not only at the personal level, but more at the social level. So there are different dimensions of learning we can explore. And there are different ways we can track these different dimensions. For instance, we can use sensors, or we can use trackers to collect all this type of information. The context that we wanted to explore is self-regulated learning. Nowadays, we all have to learn ourselves a lot of things, and we all have to deal with a lot of information. We sit in front of our laptop and we struggle to make sense of all the information that we have. And of course, self-regulated learners don't have any guidance, any feedback on what they do, and any support. And at the end of the day, now we feel a little bit now drawing into this amount of information. So in this context, we are proposing now an approach which is inherited somehow from machine learning. And this is a little bit a vision because has, of course, several limitations. But the intuition is that if we can collect multimodal data and we can pair this multimodal data with learning performance, and this would basically would allow us to learn predictive models that are able to predict learning performance out of the historical data. So it's particularly important the division that I make between the multimodal data, which is what I call the input space, and the output space, the learning performance. The approach that we decided not to use in our experiment start with a set of questions, first of all. The first one is, the main overarching question is, how can we store, model, and analyze multimodal data to predict learning performance? And we define 3 sub-questions. First of all, what architecture allows to collect multimodal data in a scalable, efficient way? Then, what is the best way to model multimodal data in order to apply supervised machine learning? And third question is how machine learning models, what is the best machine learning model we can use in order to make learner-specific prediction and recommendations. The participants that we used in our experiments are PhD students at the Welten Institute, and all of them are can be considered both can be considered self-regulated learners, and they specialize in different disciplines, and they have different setups also on their work, and they work in different time, different tasks. They also use different operating systems on their laptops. Our experiment consisted in 3 phases. The first, a pre-test where we tested all the system architecture, then a training phase where we collected the data, and then a validation phase where we collected the data and we generated a prediction. I said that learning is happening in different spaces, but I wanted to explain a little bit what is our input space. So first of all, we see the learner doing activities in a context, and we decided to take these 3 modalities. First of all, we wanted to model somehow, collect data from the body using Fitbit heart tracker. And we collected heart rate and steps. Then we also wanted to collect activity data, and we used rescue time for collecting the activity, so the specific software that people were using on their laptops. But also we wanted somehow to model the context, and for this reason we used weather data also to model the context of learning. And this would give us, in our opinion, a much better picture of the learning context where the learner is acting. So this is what is the input space, but I also talked about the output space. For me, what we used in our study is the concept of flow. Csikszentmihalyi in 1972 developed this model, the flow, which is a mental state of operation that happens whenever we are doing a task which is particularly challenging, but at the same time we are quite prepared to do that task. And so the flow, when people are in the flow, they forget they are in this phase where they are really productive. And we thought that this could be a good idea for self-regulated learners to maximize the learning performance. So on the left, on the left end, you can see the theoretical model developed by Csikszentmihalyi. On the right side, you see now what the empirical measurements that we took. But how did we sample this measurement of the flow? We developed an application called Activity Rating Tool, which is a scalable web application, which also runs on mobile. And basically, the participants had to rate hourly their level of productivity, stress, challenge, and abilities. So they had to answer with these sliders that could give a value from 0 to 100. They had to answer these questions. How productive was the last activity? How stressful was the last activity? But also, how challenging was the last activity? And how prepared did you feel for the last activity? And these challenge and abilities, as I showed one second ago, make up this one indicator, which is the flow. One comment that we had is that this application was particularly seamless, so particularly easy to use, and the rating didn't take so much time. A little bit, an overview of what the data collection looks like. So I explained a little bit the data model. So we collect sensors from the Fitbits, such as heart rate, step counts, but also activity data. So the softwares, the people that were using with their laptops, and the duration in time. Also weather data, temperature, humidity, pressure, precipitation, weather type, but also the ratings that were people giving. And we combine all this data into a data model. The way we model this data is Experience API, and I'm showing here a poster, XAPI recipes, that was actually a Best Poster Award last year at last LAK', and shows how to compose this Experience API statements using a subject, verb, and object. And this is a very interoperable way of storing educational data. This data collected goes somehow in a sort of data journey. So from the learner, we see that we collect data and we put that in the learning record store. But the idea is to continuously process this data and somehow to close the loop with the learner, so visualize somehow the data back to the learner. So this is a quite simplified journey of the data that, however, hinders a more complicated architecture, of course. This graph is particularly difficult to read, so I will try to make it a little bit easier, showing how that relates for our data journey. The data collection is responsible for the data collection where what we call the learning pulse server and the learning record store. That basically what they did is pull in the data from the third-party APIs, make up these experience API triples, and putting them in a learning record store. So this was a particularly important strength point of our application, because this data architecture ended up to be very scalable in a way, so could combine a lot of data from the sensors and avoiding collisions and being quite fast, and for the fact that it's using Experience API is also interoperable. The data collection is one leg. The data processing is the other leg. Together with this data collection and the learning record store, we also developed this application to continuously process the data. We developed that in Python. And that then, therefore, pulls the data from the learning record store and applies several different data analysis techniques that make somehow are able to make predictions, and the idea is that we should feed these predictions back to the learner. I'm not going to talk about this green link, so the data processing, which become visualization. This is not really part of my paper because we didn't develop quite much the visualizations, but the idea is that we can use this visualization to feed them back to the learner. I want to focus now on the data analysis because I think it's quite important and relevant. From the Experience API data format is quite an important, quite a useful way of storing data, but this probably not the best way to analyze that. So we decided that we wanted to somehow transform these XAPI triples in a different representation. And we decided to use this time series tabular representation. And we decided to go for 5-minute intervals. So each learning sample would constitute a 5-minute interval having different attributes. And all these attributes are basically time series. So we ended up having 9,400 learning samples constituting of 29 different attributes. And in that way, we could reach a reasonable amount of learning samples, and that this representation is somehow easier for machine learning in order to run machine learning techniques. But of course, this representation implied a lot of problems that we had to face and to solve. First of all, how to align the different time series, which they come in different granularity, into aligned representation. For example, heart rate, we had to find a way to compress the signal in some compress the 5-minute signals, as is shown in this graph, into some numeric features. And we decided not to use the mean of the signal, the maximum, minimum, standard deviation, average change to extract features from the heart rate time series. The second issue we faced is that activity data ended up to be very sparse. So we were tracking what the people were doing on their laptop, and of course, each people uses different applications. So that means the number of applications is quite large, and it's also quite different from learner to learner. So we decided to reduce the number of applications by grouping into different clusters. And that would somehow solve the problem of sparsity, which is a very big problem. As you can see on the left-hand side, you can see this long tail of very applications use it probably one time or less, yeah, about one or few times. So in this way of grouping, basically the number of applications reduce, and in this way we could also compare the different learners together. Then another problem we faced is the fact that there is a trade-off between the number of labels you can collect, so the number of time you can ask people to rate, with the seamlessness of data collection. And for this thing, there was no solution, unfortunately. Then also we had to face with different type of data. From one side of fixed effect data, like heart rate, against random effects data, like, for example, activity data. And you can see in this graph quite clearly the fact that these voluntary action, like using, for example, Skype, is a random effect, so it doesn't depend from the previous intervals, while the heart rate is a fixed effect. So we had to take into account these two different types of data. And the solution that we found, we used mixed effect linear model, which is basically a way of taking into account both fixed and random effects and somehow preserving the specificity of each learner. And in this way, we could combine the two different types of attributes, and we could generate prediction for each learner. Lastly, the problem that we faced is also the fact that the learners are all rating very differently, as this graph shows. And for overcoming this issue, we used normalization with respect to each learner. So the prediction that we had to normalize somehow with respect to each learner. Some conclusions. Coming back to the research question, the first one was regarding the architecture. And the architecture that we developed was able to import a great number of sensor data, combine this sensor data with self-report, and programmatically transform this XAPI sort of data into our representation suitable for machine learning, to train models that are able to predict the labels, the indicators given by the learners. And also to compare whether the prediction how they compare with the actual values that people give. The second question was regarding how to represent this multimodal data, and we used this tabular representation, this multiple instance representation, where each learning sample constitutes a 5-minute interval that's suitable for machine learning. Then the third research question is how to represent multimodal data in a best way. Which model was suitable for multimodal data. And we discovered that the linear mixed effect models is a model that allows to taking into account data specific for each learner, distinguish between the fixed effects and the random effects, and take also categorical data into account. Of course, this approach has a limitation. You may wonder, but what about the actual prediction accuracy? I'm quite honest to say that unfortunately we achieved a not very high prediction accuracy. We used R-square test with our mixed linear effect model, and we discovered the stress is probably not the indicator that we can predict the best. Not so much the others. In addition, we see some real-time issue. The current synchronization with Fitbits has some problems. The virtual machine had also some limitation. Then we also had to rely to third-party APIs, and this is also another limitation. And then we also had to group manually the activity data that I show you were quite sparse, and this is also not a very scalable solution. However, there's a lot of opportunities, I think, with this approach. First of all, it's an attempt to make data-driven somehow multimodal data. And so today we have seen in the presentations and the keynote that several different sensor data can be collected, but that still faces the limitation that there should be human interpreting that data. In this approach, we are trying to make this interpretation somehow automatic with machine learning. That means that there's no longer a human that needs to decide somehow what is the sensor and the modality which matters the most on predictive learning, but is somehow the learning algorithm that decides what is important. Then another thing is that real time can actually be used for real-time data can actually be an added value, because the long-term aim is to give people timely feedback on how they are learning. Then visualization, I did not cover this, but they can be used. And one example you can see that is the feedback cube, and to show in the colors how people are performing. And the other thing is that the data collection was quite seamless. And then, of course, we collected a data set that we can research on, and we developed an architecture which is reusable. So that was my presentation. Thank you very much for listening. I invite I take the occasion to invite you to my poster presentation that will happen this afternoon. Thank you very much.
Thank you, Daniele. Are there any questions?
Just a question about modeling sensor data using XAPI. What do you do if you get a lot of sensor data? You are mentioning heart rate, which could be easily 100 more sensor data per second. We don't want to model each data as a specific XAPI statement.
You're completely right. This, I think, we think this one limitation of Experience API. Experience API work with the structure subject, verb, object. And this subject, verb, object should be meaningful. In the case of heart rate, there is no actually verb we can express with that. The verb we use this, the learner has experience a certain level of heart rate. And we put every single heart rate value, which was, by the way, 5 seconds of frequency, we put that as a single XAPI statement. But we recognize that's not probably the best solution, because XAPI should express meaningful actions that the learner take, and not value for each and every sensor data. So in this respect, I agree with you. That's probably not the best approach.
I think it's about processing and aggregating sensor data to get some meaningful data in the learning context before modeling it as an XAPI statement.
Could also be a way, yes.
Bill?
Just a comment, if you'll press the button beneath your microphone, you can broadcast.
Thank you, Phil. Other questions?
Why did you discard heart rate variability? It seems to be an indicator from what we know from literature that would be worthwhile checking, and I just noted on your slide that discarded.
Yeah, the reason why we discarded it was because the API, we had to rely on the API that Fitbit could offer, and which give us only a value every 5 seconds, which is not enough to calculate heart rate variability, unfortunately. And that's, I agree with you, that's a bit problem.
Yeah, do you know how the Fitbit actually measures heart rate and steps taken?
Yes, I know. I mean, it uses some sort of light sensor, so depending how
So my question really is that often these commercial products are like black boxes. You don't know how they're calculating these measures. You don't know how reliable they are at times. And they do that because that's proprietary to their device. And they're usually not going to tell you.
Yeah, there are actually some studies on that. And Fitbit is probably one of the most reliable sensors in commerce. But I'm not entirely sure. I mean, this was not really the focus. But Fitbit, I think that it releases also its algorithms, so for inspection, and it's somehow certified to be reliable. Yeah, or at least it's one of the best in the commerce. Yes.
I think we have one more question up
I have a question about the modeling approach that you took. I was a little confused by the distinction that you made between fixed and random effects given the data source that you were pointing at. Why would it make more sense to model Skype calls as sort of a Gaussian rather than as a fixed effect? I mean, those terms seem to didn't make much sense to me. The other thing is, given that you have time series data, why not use a time series model that would have sort of lagged predictors in there to look at changes, especially when you're looking at heart rate. Change in heart rate might be very important rather than heart rate in general.
Yes, sure. The reason is that we were tracking the activity that people were doing on the laptops. And we had this type of data showing, for example, the amount of seconds that I was using Skype. And that type of data, as you can see from this graph, is not a time series. You could use Skype for 10 minutes and then stop and then reuse it for other 30 minutes. It's really random. It's actually depending on the learner will to use Skype. It's not a measure that you track on the background, which continuously give you information like the heart rate sensor.
Just to clarify, I agree, yeah, it's right to model that, the length of the calls as a random effect. But if you're looking at over time, how often you use Skype, maybe as a way of getting help from other learners, other PhD students, wouldn't that be a time series event?
I think so, yes, but the problem that you incur with this, I think, is sparsity. So what if you're not using Skype at all? Then you always have 0, I guess.
That just seems to be the point of measuring data longitudinally, right?
Yeah,
to
exactly.
Look at changes in time, yeah.
But sparsity, by the way, was one of the biggest issue we had to face. And just to conclude, one of the insights we got is that whenever you take a sparse variable into account, that affects negatively your model. And whenever, on the other hand, if you take a continuous variable into account, for some reason that would improve the prediction accuracy of the model.
Okay, thank you very much.